A polynomial function is a mathematical sum of terms consisting of variables raised to whole number exponents and multiplied by a constant coefficient. The leading coefficient is the coefficient of the term with the highest degree in the polynomial. It is the first number in the expression that multiplies the variable raised to the highest power.
Multiplicity determines whether the graph of a function passes through the x-axis or touches the x-axis and turns. This can also determine the number of valleys and hills on a graph.
Vertex is the highest or lowest point on a parabola, which is basically the turning point of a quadratic.
Synthetic division is a shorthand method of dividing polynomials by linear binomials in the format of x minus a by writing down only the coefficients of the polynomials. For example, you are able to divide polynomials by x plus 1 because x plus 1 is linear. However, you're not able to divide polynomials by x to the third minus a because it is not linear. U sub is a way to simplify equations by substituting variables into an equation. The most common variable is u, followed by v. However, you do not need to use these variables. In this example problem, the student successfully substitutes u in, which allows for them to substitute and simplify the equation. However, in the non-example, the student substitutes it wrong, which changes the value of the equation. Rational root theorem is a way of narrowing down the possible roots or solution to equations by the formula p over q, where factors of the constant p are divided by the factors of the leading coefficient q. For example, the rational root theorem is applicable whenever the leading coefficient and constant are both rational. However, the rational root theorem is not applicable whenever the leading coefficient or constant are non-rational.
The formula x equals negative b plus or minus square root of b squared minus 4ac over 2a, which gives solutions or roots of equations in the form ax squared plus bx plus c equals 0, where a is not equal to 0, can be used when methods like factoring or perfect squares are not viable. And some working examples would include quadratic equations, and a non-example would be a cubic equation. A polynomial in one variable is written in standard form when the terms are in order from greatest to least degree. An example of this would be x squared plus x plus 3, and a non-example of this would be x plus x squared plus 3.
Vertex form is the formula that makes the vertex of a quadratic very easy to see, and it's written as y equals a times x minus h squared plus k, and for the vertex is at hk. An example would be y equals 2 times x plus 1 squared minus 5, where we can immediately tell that the vertex is negative 1, negative 5. However, a non-example is something like y equals x squared plus 3x plus 4, which is in standard form, so you cannot tell the vertex by just looking at it. The remainder theorem tells us that when a polynomial is divided by a linear factor x minus c, the remainder will equal f of c. In this example polynomial divided by x minus 2, the remainder will be f of 2, which is equal to 7. In this non-example polynomial divided by x squared minus 2, it violates the theorem because the divisor is not linear in the form of x minus c, so f of 2 will not represent the remainder. Factor theorem says that if f of c equals 0, then x minus c will be a factor or root of the polynomial. This is seen in the example polynomial where f of 2 would equal 0, so that means that x minus 2 is a factor or root. However, in the non-example, if f of 1 is equal to 2, then x minus 1 would not be a factor or root because the remainder is not equal to 0. Factored form writes a polynomial as a product of factors, making the roots or zeros very easy to see. In the example, the zeros will be x equals negative 1 and 4. In the non-example, you cannot tell the zeros easily because it is in standard form. Complex roots are the imaginary non-real solutions to a polynomial equation. In this example equation, it has complex roots at x equals 2i and x equals negative 2i. In this non-example equation, it has real roots at x equals negative 3 and 3, so there are no complex roots.
Firstly, to graph the quadratic function, we can first change the original equation from standard form into vertex form, which allows us to understand it's just the parent function shifted 6 units up. Knowing this, we can graph the equation. In this graph, there are no x-intercepts because the graph does not intersect the x-axis. The end behavior is, as the limit of x approaches infinity, fx increases. However, as the limit of x approaches negative infinity, fx still increases. In this equation, The domain of x is all real numbers. The range is y is greater than or equal to 6. There are no zeros or x-intercepts because the graph does not touch the x-axis. However, the y-intercept is 0, 6. For the extrema, there are no relative or absolute maximum because there's no increasing to decreasing intervals in this equation. However, there is a relative and absolute minimum because there's one turning point where it turns from decreasing to increasing at y equals 6. The increasing intervals are from whenever x is greater than 0 and decreasing from whenever x is less than 0. In the case of the cubic graph, we're already given pretty much the x-intercepts, which allows us to approximate and sketch a graph. By solving the equation for the x-intercepts, we were able to find out that x equals -1, 2, and 3, giving us our zeros and x-intercepts. After looking at it again, each of these x-intercepts only occur once, which means they're a multiplicity of 1, and each are odd, which means they will only cross the x-axis. For end behavior, as the limit of x approaches infinity, fx decreases. As limit of x approaches -infinity, fx increases. The domain of this equation is x equals all real numbers. The range is y equals all real numbers. Zeros are at x equals -1, 2, and 3. The y-intercept is 0, -6. The x-intercepts are located at -1, 0, 2, 0, and 3, 0. For extrema, there is no absolutes because the graph goes on continuously, which means they both approach infinity, which means they cannot be counted. For relative maximum, the y is equal to 0.87. However, the relative minimum is y equals -6. For the increasing intervals, x increases from 0.13 to 2.53. However, when it decreases, x decreases from -infinity to 0.13 to 2.53 to infinity. In the case of the quartic formula, we can solve for the x-intercepts to solve and approximate a graph. By solving for the x-intercepts, we're able to determine that the zeros of this equation are x equals -2, 0, and 1. In this equation, -2 occurs twice, which means the point -2, 0 is a multiplicity of 2, which means they will have even behavior, which further means that it will only touch the x-axis but turn around at this point. However, for 0, 0, and 1, 0, they are both multiplicity of 1, so at these points, the graph will appear straight through the x-axis and continue straight going through. However, for end behavior, as limit of x approaches infinity, fx will increase. However, as limit of x approaches -infinity, fx will still increase. The domain of this equation is x equals all real numbers. The range is y is greater than or equal to -1.6. At this equation, zeros are x equals -2, 0, and 1, multiplicity 2 for -2, and multiplicity 1 for the rest. The y-intercept is 0, 0. The x-intercept are the zeros, which are -2, 0, 0, 0, and 1, 0. For the extrema, there is a relative maximum at y equals 2.07, and the relative minimum at y equals 0, and y equals -16226. However, there is no absolute maximum because the graph goes on infinitely in the upwards direction. There is an absolute minimum, however, at y equals -1.6. This graph is increasing when x is an element of 0.13 to 2.53. This graph is decreasing when x is an element of -infinity to 0.13, unity 2.53 to infinity.
Solve f of x equals to x to the power of 4 minus 5x to the power of 2 plus 4. So the first step will be to use u sub, so we let u equal to x squared. Then after using u sub, we can factor out f of x equals to u minus 4 times u minus 1. We can then factor x squared back in for u and get x squared minus 4 times x squared minus 1. And by factoring that out, we get f of x equals to x minus 2 times x plus 2 times x minus 1 times x plus 1. And then we can set f of x to 0 to find the roots, and in the end we'll get x equals to -2, x equals to -1, x equals to 1, and x equals to 2. Solve p of x equals to 3x cubed minus 10x squared plus 10x minus 4. So first, if we want to use rational root theorem, we will need to find all possible values of p over q. As you can see, we did that, and then I decided to use 2 to try and find the root, and at the end we get a 0, meaning that positive 2 is a root of p of x, 3x cubed minus 10x squared plus 10x minus 4. So the remaining digits will be 3x squared minus 4x plus 2, and since we cannot use factoring, quadratic formula will be the way we find our other values of x. And after substituting every single value of a, b, and c into quadratic formula, we get x equals positive 2 plus or minus square root 2i over 3. So that means all possible answers for x will be x equals to 2 minus square root of 2i over 3, 2 plus square root 2i over 3, and that will be all three answers that you can get. Solve h of x equals to x cubed minus 5x squared plus 2x plus 8. So the first step will be to factor it out. So we get h of x equals to x minus 4 times x minus 2 times x plus 1. And we want to use rational root theorem, so we will need to find p over q. So the values of p over q would be plus minus 1, plus minus 2, plus minus 4, and plus minus 8. So we decided to try 4, and as you can see, it ended up resulting in a 0, meaning that x minus 4 is a factor of h of x, because while using synthetic substitution to divide x minus 4 from h of x, it shows that h of 4 is equal to 0. Therefore, x minus 4 is a factor of h of x.
A laboratory supply company is designing a new rectangular box in which to ship glass pipes. The company has created a box with a width 2 inches shorter than its length and a height 9 inches taller than twice its length. The volume of each box must be 45 cubic inches. What are the dimensions? Our first step is to define the variables. We know that L will be the length of the box, and the width is already said to be 2 inches less than the length, so W will equal to L minus 2. The height is said to be 9 inches more than twice the length, so H will equal to 2L plus 9, and it already says that the volume must equal 45. Using the volume formula, we can express the volume as a function of L, and after calculating the value of L, we can use the value to substitute it back into the equations of weight and height to find the other dimensions. Next, we will substitute the variables that we have already identified, which are the width and height, into the volume formula, and we already know that the volume must be 45 cubic inches, so we can set that equal to 45. And we can expand the polynomial and combine like terms, and then set the polynomial equal to 0. Now we will find a root utilizing the rational root theorem. We already know that the leading coefficient is 2 and the constant term is 45, so we use those factors using the constant factor over the leading coefficient factor to find possible candidates. Now we will try L equals 3 and use direct substitution to find that the polynomial equals 0, which means that L equals 3 is a root of the polynomial, which also means that L minus 3 is a factor of the polynomial. Next, we will divide the polynomial by L minus 3 to find the remaining factors using synthetic division. The remainder will equal to 0, so we will be left with a quadratic 2L squared plus 11L plus 15, which can be further factored into L plus 3 times 2L plus 5, and combining our other factor L minus 3, we will have the full factorization of the cubic polynomial. Next, we will solve each factor using the zero product property, and we'll find that the three solutions are L equals 3, negative 3, and negative 2.5. Next, we'll apply physical constraints with the domain restriction greater than 0 because all dimensions must be positive, and we'll find that L must be greater than 2, and only L equals 3 is greater than 2, so it will be the only physically valid solution. Now that we know that length is equal to 3, we can substitute it back into the width and height equations that we have already identified to find that width is equal to 1 and the height is equal to 15. And substituting all these values back into the volume formula, we'll get 45, which matches the required volume. Therefore, the rectangular box with a volume of 45 cubic inches has a length of 3 inches, a width of 1 inch, and a height of 15 inches.